Hello my dear students, I welcome you all for this lecture. So we will study the chapter number 13 Nuclei Part 3. So in this we will study the radioactivity. So what is meant by radioactivity? So before that we will go through the radioactive rays. So what is meant by the radioactive rays, or it is also known as Becquerel rays. Okay, so these are the radiations emitted during radioactivity. So actually the radioactivity is a here natural process, okay, that is emits the continuous radiations, okay, that emits the continuous radiations from the heavy elements like uranium, thorium, radium, etc. Okay, and the whatever the rays, okay, the radioactive rays, or that is the Becquerel rays, okay, that are the radiations emitted during radioactivity. So the radioactivity rays, or it is also known as Becquerel rays, where the Becquerel is the scientist name, okay. So radioactive rays, okay, that are the emitted rays during radioactive process. So next one, what is meant by the radioactive elements? So radioactive elements, these are the substances which exhibits radioactivity, okay. So here the heavy atoms, okay, the heavy substance like uranium, thorium, radium, actinium, okay, etc. These are the examples for radioactive elements, okay. So the heavy elements or the heavy substance that will be exhibits radioactivity, that are known as radioactive elements. So we'll see what is meant by the natural radioactivity. Okay, so these are the naturally occurring elements. Okay, so the radioactivity is also process, that is also the natural process, and the radioactivity was discovered by Henry Becquerel in 1896. Okay, it is discovered by Henry Becquerel in 1896. The term radioactivity was introduced by Marie Curie. Okay, and that word or that term radioactivity, that is introduced by Marie Curie, and the emission of radiation is not affected by external agencies like temperature, pressure, electric field, magnetic field, etc. Okay, so in this radioactivity process, okay, the emission of radioactive radiations is not affected by external agencies, okay, like temperature, pressure, electric field, magnetic field, etc. So the radioactivity takes place inside the nucleus, okay. So because of that reason, okay, it is known as what? The nuclear phenomena. Therefore it is a nuclear phenomena because it takes place inside the nucleus, okay. So radioactivity is a process that takes place inside the nucleus. Because of that reason it is known as what? Nuclear phenomena. And the radioactivity is irreversible process, okay. So here in this slide we'll study the radioactive rays or Becquerel rays, okay. These are what? These are the radiations emitted during radioactivity. And radioactive elements is what? These are the substance which exhibits radioactivity, okay. It is a substance like heavy substance uranium, thorium, radium, actinium, etc. And it is a natural process, and it is discovered by Henry Becquerel in 1896, and that term radioactivity was introduced by Marie Curie, and the emission of radioactive radiation is not affected by external agencies like temperature, pressure, electric field, magnetic field, etc. And radioactivity takes place inside the nucleus. Because of that reason, it is a nuclear phenomena, and the radioactivity is a reversible process. So, because of this, okay, the we'll see the what is meant by the radioactivity. So, we'll study what is meant by the radioactivity. So, the radioactivity, it is a spontaneous nuclear disintegration of certain heavy elements with the emission of certain radiations. Okay, it is the spontaneous, okay, continuous, without stopping, the continuous, the this emission of radiations, okay, the continuous process, and that is a disintegration of the heavy elements. Okay, so continuous, the emission of certain radiations, is that process is known as what? The radioactivity. So radioactivity is defined like this: it is the spontaneous nuclear disintegration of certain heavy elements with the emission of certain radiations. So next one, what is meant by radioactive decay law? Okay, so the statement, it is the rate of disintegration of radioactive substance at any instant is directly proportional to the number of atoms present in it at that instant. Okay, it is the rate of disintegration of radioactive substance at any instant is directly proportional to what? The number of atoms present in it at that instant. Suppose n be the number of atoms present in a radioactive substance at a given time, then if the Dn be the number of atoms disintegrated in the time interval dt, then according to decay law, it is dn by dt is directly proportional to n. Okay, so dn is the number of atoms disintegrated by the time interval dt, that is dn by dt is directly proportional to the number of atoms present in that substance, that is capital N. So the dn by dt is directly proportional to n. If you should take the proportionality sign to equal sign, then you should take one constant. Okay, so therefore we will take dn by dt is equal to minus lambda into n, where the lambda is what? It is a constant of proportionality, or also known as the decay constant, and the negative sign indicates the number of atoms decreases with time due to disintegration. Okay, so negative sign indicates that the number of atoms decreases with time due to disintegration. Therefore, the negative sign, okay, that will be indicates the always decreasing of number of atoms, okay, because of spontaneous emission, okay, that process, okay, continuous emission of radiation process, okay, the number of atoms will be decreases with time. Okay, so that is the dn by dt is equal to minus lambda into n. So we'll see what is meant by the activity of a radioactive substance. Okay, or it is also known as decay rate. the activity of radioactive substance, or it is also known as decay rate. Okay, it is the rate of disintegration of radioactive substance. If Dn atoms disintegrates in time dt, then activity A is equal to dN by dt, where A is equal to lambda into N. Okay, it is the rate of disintegration of radioactive substance. If the Dn atoms disintegrated with the time dt, then the activity is A is equal to dN by dt. Okay, where the A is equal to lambda into N. Okay, so because of the previous relation, okay, so that is dN by dt is a lambda into N. Okay, that relation will take A is equal to lambda into N. Okay, so the units, we'll see the units of radioactivity. Okay, what are the units of radioactivity? So the becquerel is the SI unit of activity. Okay, the becquerel is the SI unit of activity. Becquerel is the scientist name also. Okay, so it is also, we'll write the capital B small q, BQ, becquerel. Okay, it is the SI unit of activity. And the Curie CI is the most commonly used unit of activity. Okay, so becquerel BQ is the SI unit of activity, and the Curie CI is the most commonly used unit for activity. And activity is what? It is the A is equal to dN by dt, rate of disintegration of radioactive substance. Okay, so here the will define what is meant by the becquerel. Okay, or one becquerel means what. So here the relation A is equal to dN by dt when A is 1 becquerel, when dN is 1 atom and dt is for 1 second. So therefore the activity of radioactive substance, okay, activity of radioactive substance is said to be 1 becquerel when the one atom disintegrates in 1 second. Okay, so the activity of radioactive substance is said to be 1 becquerel when the one atom disintegrates in 1 second. Then we'll see the Curie. What is meant by the one Curie? Okay, define Curie. So it is the activity of radioactive substance. Okay, activity of radioactive substance is said to be 1 Curie when the 3.7 into 10 raised to 10 atom disintegrates in 1 second. Okay, so that is the when the activity of radioactive substance is said to be 1 Curie when 3.7 into 10 raised to 10 atom disintegrates in 1 second. So therefore the becquerel is, it is the SI unit of activity, and Curie is also one commonly used unit for activity, and the 1 Curie or 1 becquerel, okay, will defined like this. The 1 becquerel is the activity of a radioactive substance is said to be 1 becquerel when the one atom disintegrates in 1 second, and the 1 Curie is a activity of a radioactive substance is said to be 1 Curie when 3.7 into 10 raised to 10 atom disintegrates in 1 second. Okay, so these are about the units of radioactivity. Then the consider A is equal to dN by dt, this relation. Okay, if dN by dt is equal to 1 atom per second. Okay, so if the dN by dt is equal to, that is 1 atom per second, then the A is equal to 1 becquerel. Okay, so becquerel is a, suppose dN by dt is equal to 1 atom per second. If dN by dt is equal to 3.7 into 10 raised to 10 atom per second, then the activity A is equal to 1 Curie. Okay, if dN by dt is equal to 3.7 into 10 raised to 10 atom per second, then the activity is equal to A is equal to what? 1 Curie. Then the activity of 1 gram of radium is 3.7 into 10 raised to 10 atoms per second. Okay, so 1 gram of radium is 3.7 into 10 raised to 10 atom per second. Therefore, the Curie is the activity of 1 gram of radium. Okay, so the Curie is what? It is the activity of 1 gram of radium. Therefore, the relation between Curie and becquerel is what? 1 Curie is equal to 3.7 into 10 raised to 10 distance per second. But 1 distance per second is 1 becquerel. Therefore, the 1 Curie is equal to 3.7 into 10 raised to 10 becquerel. So, it is a very important relation. So, that is the 1 Curie is equal to 3.7 into 10 raised to 10 becquerel. Okay, so 1 Curie is equal to 3.7 into 10 raised to 10 becquerel. The next one, we will see the expression for the number of nuclei remaining in a radioactive substance after a certain time n is equal to n naught e raised to minus lambda t. Okay, suppose the number of nuclei remaining in a radioactive sample after a certain time. Okay, then the decay law says, radioactive decay law says, the number of radioactive decay law, okay, that will be the number of nuclei undergoing decay per unit time, okay, that is proportional to the total number of parent nuclei present in the sample at that instant. Okay, suppose the radioactive decay law says that the number of nuclei, okay, undergoing decay per unit time, okay, is directly proportional to the total number of parent nuclei present in the sample at that instant. Okay, so that is the total number of nuclei present at that time is equal to what? The It is the number of nuclei undergoing decay per unit time. Okay, so that is the dN by dt is equal to minus lambda into n. Okay, so the previous relation we have studied that the dN by dt is equal to what? Minus lambda into n. Suppose this is equation number 1. Then here the dt, you LHS side to, which you should take RHS side, okay, and n you take this side, okay, therefore the dN by n is equal to minus lambda into dt, okay, that is the dN by n is equal to minus lambda into dt. Now integrating both sides of the above equation. So the above equation is what? dN by dt is equal to minus lambda into n. So this equation we will write as a dn by n is equal to minus lambda into dt. Okay, so integration of n naught to n dn by n is equal to minus lambda integration of t naught to t dt. Okay, so that is we'll take as a ln n. Okay, that is the limits as a n naught to n, and after that the the limits as a n naught to n. So that is the ln n, that is limits n naught to n is equal to minus lambda t, that is t naught to t. Okay, so here that we will write as a ln n minus ln n naught. Okay, so we'll put first upper limit as a n, so that is ln n minus ln n naught is equal to minus lambda. First you should to put the t as a t minus t naught, upper limit minus lower limit. Okay, so that is the ln n minus ln n naught is equal to minus lambda t minus t naught. Suppose this is equation number 2. Then if the n naught is the number of radioactive nuclei in the sample at some time t naught, then the n is what? N is the number of radioactive nuclei at time t. Okay, n is the number of radioactive nuclei at the time t. When the t naught is equal to 0, then n is equal to n naught. Okay, suppose the t naught is equal to 0 for t naught is equal to 0, and for n as a n naught, then ln n minus n naught is equal to minus lambda into t minus t naught. Okay, where the here that is ln n by n naught is equal to minus lambda into t minus 0. Okay, so that is n is equal to n naught e raised to minus lambda into t. Okay, so here in this relation, n is equal to n naught e raised to minus lambda t, okay, is the expression for the number of nuclei remaining in the radioactive sample after certain time. Okay, that is the after certain time the n is equal to n naught e raised to minus lambda into t. Next one we'll see the what is meant by the radioactive decay constant. Okay, so radioactive decay constant, it is the reciprocal of the time during which the number of atoms of radioactive substance reduces to 37% of initial number of atoms. Okay, so it is the reciprocal of what? Time during which the number of atoms of radioactive substance reduces to 37% of initial number of atoms. Okay, then we'll see the half-life period of radioactive element. Okay, it is the time during which the half of the atoms of radioactive substance undergoes disintegration. Okay, suppose you should take the full atom, okay, the full substance that is having the so many atoms, and for that you should consider the half. Okay, suppose you should consider the half of the that atom. Okay, and if that will be that radioactive half of the atom of radioactive substance undergoes the disintegration, that is known as what? The time during which the half of the atom of radioactive substance undergoes disintegration. Okay. So next one, that is the expression for the half-life of a radioactive element. Okay. So we will study the expression for the half-life of the radioactive element, where the half-life is what? Half-life period of radioactive element is what? It is the time during half of the atom of radioactive substance undergoes disintegration. Then the half-life period of radioactive substance is the time taken by the sample to reduce the half of its original value. Okay, so half-life period of a radioactive substance is a time taken by the sample to reduce the half of its original value. Okay, that is T half is equal to 0.693 divided by lambda, where T half is the half life and lambda is the decay constant. Okay, lambda is what? Decay constant. So how to get this? T half is equal to 0.693 by lambda? That expression we will study now. Okay, so we will obtain the expression for half-life. Consider the relation n is equal to n naught e raised to minus lambda t. Okay, so where n is what? N is the number of atoms at a given instant of time t. N naught is the initial number of atoms in a radioactive substance, and the lambda is a decay constant. Suppose here it is the initially, okay, the number of atoms present in that radioactive substance. Suppose it is a one radioactive substance, okay, in that the n number of, okay, atoms will be present in it. Initially it is a n naught is the initial number of atoms present in that radioactive substance. Okay, so initially how much amount of the atoms will be present in the substance. Okay, and suppose you should make that the full atom or full substance to half of it. Okay, to make this half, okay, you should make the T as a T half and N naught as a N naught by 2. Okay, T as a T half and N naught is a, okay, here the N is a N naught by 2. For first, the number of atoms will be N is equal to N naught for first substance, and when you make it as a half, okay, then the N is equal to N naught by 2. Then the relation you should consider, N is equal to N naught e raised to minus lambda into T. Suppose that is equation number 1. And if the N naught is the initial number of atoms in a radioactive substance and N is the number of atoms at a given instant T and lambda is a decay constant, for the half-life period T is equal to T half and the N is equal to N naught by 2. Okay, so that is the time T is equal to T half and N is equal to N naught by 2. Then the relation from equation number 1, N is equal to N naught e raised to minus lambda T. Okay, you should write N naught by 2 is equal to N naught e raised to minus lambda T half. Okay, so that is minus lambda T half. Then the n naught by 2 is equal to, suppose that is n naught by e raised to lambda. Okay, here suppose you should take the n naught by 2 is equal to n naught e raised to minus lambda t half. Okay, then the n naught by 2 is equal to n naught divided by e raised to plus lambda t half. Okay, this is a minus for a numerator. If you will take for denominator, that is a plus lambda t half. Then the e raised to lambda t half is equal to 2. Okay, if we will cancel n naught n naught. So 1 by 2 is equal to 1 by e raised to lambda t half. Therefore, 2 is equal to e raised to lambda t half. Okay, but we'll see the relation e raised to x is equal to y. Then the x is equal to log y to the base e. Okay, the relation is what? E raised to x is equal to y. Then x is equal to log y to the base e. Therefore, the lambda t half is equal to log 2 to the base e. Okay, so that is lambda t half is equal to log 2 to the base e. Then that is a lambda t half is equal to 2.303 log 2 to the base 10. Okay, so if the e raised to x is equal to y, okay, here in this relation e raised to x is a lambda t half. Okay, if e raised to x is lambda t half is equal to 2, then therefore lambda t half is equal to log 2 to the base e. Then the lambda t half is equal to 2.303 into log 2 to the base 10. Okay, so that is the lambda t half is equal to 2.303 into log 2 value is 0.3010. Okay, so the 2.303 into 0.3010 is 0.693. Therefore, lambda t half is equal to 0.693. Therefore, the t half is equal to, suppose, 0.693 divided by lambda. So, lambda take this side, that is the t half is equal to 0.693 divided by lambda. So, I repeat, this is the expression for what? The half-life for the full substance, radioactive substance. If for the small time, initially the time will be 0, and the suppose at a time t, okay, suppose you should take for the half life, okay, half will be the reduce that radioactive substance as a half of that, then the t becomes t half, and for n naught is the number of atoms present for the full substance. For the half substance, n is equal to what? N naught by 2. So, if you consider the relation n is equal to n naught e raised to minus lambda into t, suppose that is equation number 1, where n naught is the initial number of atoms in the radioactive substance and n is the number of atoms at a given instant t, and lambda is the decay constant. Then for the half life, okay, for the half life of that substance, okay, so the t is equal to t half and the n is equal to n naught by 2. Okay, t is equal to t half and n is equal to n naught by 2. So for this t is equal to t half and n is equal to n naught by 2, this relation, first relation you should put in that. Okay, and you should solve the equation number 1. So that is n naught by n is equal to n naught e raised to minus lambda t half, where n naught by 2 is equal to n naught divided by e raised to minus lambda t half. Okay, n naught get cancelled, and 1 by 2 is equal to 1 by e raised to minus lambda t half remains. Therefore, lambda t half is equal to 2. But use this relation e raised to x is equal to y, then x is equal to log y to the base e. From this relation, lambda t half is equal to log 2 to the base e. Therefore, the lambda t half is equal to 2.303 into log 2 to the base 10, where the lambda t half is what? 2.303 into 0.3010. By multiplying these two, you will get 0.693 is equal to lambda t half, and the lambda t half is equal to what? 0.693. Therefore, the t half is equal to 0.693 divided by lambda. Okay, so this is the expression for half-life. Thank you.